Okay, section 12.7, continuing our look at logarithms. We have two special types of logarithms. There's the common log and the natural log. And then we're going to look at, which is what's common, the change of base. And this is a formula. So we have three things to talk about in this section. Number one is logs with base 10 or e. So if it's base 10, that's what we call the common log. If it's base e, that's what we call the natural log. More on that in a second. Then we're going to look at the change of base formula. Change of base formula. And the last thing is we're going to do some equation solving. And using change of base. Now we are going to be primarily focusing, that's not an R, it's just nothing. We're going to be primarily focusing on just dealing with common log, natural log, and change of base in this section because 12.8 is all about problem solving and solving equations. So we're just going to touch on mostly just using the change of base at the end here. So as I said, the common log is log base 10 of x equals y. And it's called the common log because oftentimes we just drop the base 10 altogether. So if you see this, log x, that means you're base 10. And the reason we call it common log is because we count. So it's common because we count in base 10. In base 10. All right, we count up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we start up. Everything after that, 11, 12, 13, is really just 10 plus 1, 10 plus 2, 10 plus 3, until we get to 20, which is 2 times 10. And then we have 21 is 2 times 10 plus 1. 22 is 2 times 10 plus 2. So it's the common log. We count in base 10. That's why it's the common log. And then the natural log this is the log base e of x, which equals y. And it also gets a special symbol. It's ln x equals y. Now this is called the natural log because e, which is Euler's number, named for the mathematician Euler, the German mathematician. E is a naturally occurring number. It is one of several transcendental numbers. And transcendental, I think we talked about this, but just to refresh ourselves, remember transcendental is simply a non-repeating infinite decimal number. So pi is the other famous transcendental number. And those come up, they're not something that we created, they're not constructs of human brain power, so to speak. They are ratios that we have found in nature naturally. And so that's why this gets the natural log. And if you're wondering why is it ln and not nl, that's because the natural log, I want to say in whatever language, German or French or something like that, it's logarithm natural is how it's said. And so it gets ln. Whereas in English, we put the adjective before. So natural logarithm versus logarithm natural. But that's why it's ln. So if you see ln, know that you're working in base e. So we can do a couple problems here, a couple examples solving logarithmic equations with common logs and natural logs. So we are going to solve log x equals 12. And we're just doing this, for the basics. Since we did a lot of solving in the last section, we're gonna do a lot more in the next section. It works the exact same way. So the base you can write in here, if it helps, is 10. And so this says that 10 to the 12th equals x. And if you're curious what 10 to the 12th is, this is approximately, this is as far as we would need to take it. But just in case you're curious, this is 1584891, 1, 2, 3, 4, 5 zeros. So what is that? 15,848,900,000. No, 15,848,900,000. Approximately. Excuse me. So real big number. But we would just leave it as 10 to the 12th. In fact, your calculator probably won't even give you this. It will probably give you something like 1.58489 times 10 to the 10th, or 1.58489 E10. So all of these things mean the same. I know we haven't talked about calculator notation. Some calculators will put the power of 10. If you're on a TI calculator, the E here that you see in there means times 10 to this power. So this 10 is this 10 here in your calculator, and the E is this thing here. So they condense it. Don't ask me why. It's a calculator construction issue. And if we do a natural log, ln of x plus 2 equals 8. Again, this means that we have base e. So this means that e to the 8th equals x plus 2. And so x equals e to the 8th minus 2. And this is how we're going to leave it. E, as I said, is transcendental, which means that it's never going to be a nice number when you put it into your calculator. It's 2.7 something. So we're going to box this up and call this our final answer. So remember, this is the exact answer. And if you want an approximation, you would punch this into your calculator, and your calculator knows exactly what the value of E is, stored to a lot of decimals. I want to say like 100 decimals. You'll never see 100, but just know that your calculator is calculating it correctly. Okay, so the next thing that we're going to talk about is the change of base. So the reason we're kind of just introducing the common logs and the natural logs and then moving on to change of base is, again, because in the next section we're going to be solving a lot of equations. Common logs and natural logs, they work the exact same way, they just have these special bases. And because they have special bases, we have what's called the change of base formula. So we're going to let A, B, and C be positive or real numbers. Then log base B of A equals log base C of A divided by log base C of B. Now this works for any base C that we want, but if you take a glance at your calculators, you'll notice that we don't have, some newer calculators might, but for the most part, most calculators don't have a log base B of A button. So our C, we usually pick to be E or 10, the common log or the natural log. Because you'll notice your calculator has log base 10, it has the log button. Calculators have log x and ln x, but they don't have any other bases. Now again, some newer calculators might, but you know, this is one of the reasons we have change of base. Also, if it's the common log, we count in base 10. Powers of 10 are way easier to find than anything else. And E is just one of those special numbers. In mathematics, E becomes very important. And so we have a lot of converting to logs. Now, the interesting part of this change of base formula is this is true no matter what base we pick. So let's look at a little example to see what I mean. So let's convert log base 12 of 13. So this is something we wouldn't want to calculate by hand, and our calculator doesn't have a log base 12 button. So we need to switch this using our change of base. So we're going to let c equal 10, and then log base 12 of 13 equals the common log of a. So we take the argument, and that goes on top. So the 13, log 13. And then we take the base, our old base, and that goes on the bottom. So this is log 12. And if you punch this into your calculator, because you have log base 10 buttons, this is right around 1.0322. So now, let's let c equal e. So log base 12 of 13 becomes ln of 13, and the bottom becomes ln 12. Now if you punch this into your calculator, you get approximately 1.0322. And this is a really important thing in algebra in general, is that if you are looking, because remember, if we set this equal to x, and this equal to x, we're saying that 12 to the x equals 13, and that's the same as 10 to some power equaling 13 divided by the 10 to some power equaling 12. So let's write that out. So log 13 equals y, log 12 equals z. This is 10 to the y equals 13, and 10 to the z equals 12. These are the values. So the x that makes this equation work, this x here, this is the same x as putting this y over z. Which is really interesting that it would work this way. And as it turns out, if ln 13 equals m and ln of 12 equals n, x also equals m over n. And I know it doesn't seem like a lot, but this is actually really important because we can essentially find exponents of any base by transitioning to the base that we work with the most, the common base 10, or the special base e. And they always end up being the same thing. So to write this into a little bit more official form, what we're saying is that log x over log y always equals ln x over ln y. And this is for all x and y. Except 0, obviously. Since 0 is not in the domain of the logarithm. So that's really important. It also makes things really easy. It means that natural log and common log essentially do the same thing when you think of it in this form, in this ratio. So I have some practice problems just use some practice switching using change of base. So switch has a C, switch the following logs to base 10 or E and evaluate. So number 1, log base 5 of 3. Number 2, log base 8 of 5. And number 3, log base 9 of 4. All right, so pause the video, take a few minutes and switch these and get your answer on your calculator. You will need your calculator. And I'll start going over them now. So I'm going to switch this one to the common log. So our change of base says log 3 over log 5. And when we plug this in, we get approximately 0.683. Plugging that into the calculator. If you did ln, you should get the same answer. Approximately the same answer. I'm rounding a little bit. Here, in number 2, I'll go to ln. So this is ln 5 over ln 8. And again, you're just punching this into your calculator. You get approximately 0.774. If you did common log, base 10, you get the same answer. And then finally, number 3, I'll go back to common log. This is log 4 over log 9. And punching that into our calculator, we get approximately 0.631. So, change of base is great. It allows us to calculate logarithms with more annoying bases, because remember we're looking for powers of those bases. So there's no power of 5 that equals 3. It's going to be a fraction, a decimal power, and change of base allows us to find it relatively simple. So that's the end of 12.7. In the next section, we'll be doing lots of solving equations and solving problems using logarithms.